Oh, hello everyone. I'm very pleased to be here uh, through Insight Engineering to talk about this interesting theme in which I have worked a lot of my time. The theme is about embankment soft soils, and I'm going to discuss lots of lessons that I have learned along my career. My name is Alberto Ortigo. I am also a member of the ICE, Institution of Civil Engineers in London, and also a chartered engineer by the same institution. Well, overview. Well, I'm going to talk about lessons learned. There's a R missing there. After a 50-year experience, career, I'm going to talk about common problems, site investigation, how I learned, ground improvement solutions that have not worked, instrumentation monitoring, and in the end, some philosophical remarks I'm going to do. Uh, I hope this session, this lecture is going to last a couple of hours, and we probably make a small break, 2 minutes break after 1 hour. No. Okay, let's talk about problems. Problem I have seen along many years. Very common barrier capacity failure. I've seen this many times. This one also, it's a stitching machine to install some weak drains, which fail, to bearing failure. And embankment failure, I've seen many. This is just one example of a big failure that took place this 1994, 95, more or less. One deep failure, which I've seen, a very high embankment, and it failed, as you see here, bulging, and lots of cracks here, so it looks like to be a circular slip surface. And also, I've seen too many settlements on approach embankments. This is something that is a big problem. Sometimes they build a very good structure, but forget the ground improvement for the approach embankments. And these are interesting case which took place. The construction took place in 1978. I was very young, and I visited the site. I was in charge of a few pile load tests at this site, and at the time, I found out that we have here some 12 meters of very soft clay, and I argued about the design with the designer. You're not going to do ground improvement, etc. No, it's not necessary, etc. Just the buildings, and well, the buildings are okay until today. I visited the site last time in 2006 because I was hired to carry out some repairs, and as you see here. This was in level. At some stage, they had to put this ramp in order to access the industrial buildings here. And we see a drainage system, drainage passage box protruding towards the pavement and things like that. Let's start with site investigation. We are going to discuss a few in situ tests mainly, okay? SPT, CPT. I'm also going to discuss VSC. I'm not going to discuss the dilatometer and pressure meter because lack of time, okay? But I think those which I'm going to discuss are the main and very important in situ tests that have to be carried out in any project. Well, I'm going to refer to my books, which I wrote many years ago. I have this Soil Mechanics in the Light of Critical State Theories, which was published in 1994. And this one has nothing to do with this theme today. It's the Handbook of Slope Stabilization, which was published in 2004. Okay. Anyone wishing later on to have a copy of those books, just let me know. I'll be very pleased to send you a PDF copy. In situ tests, we can classify in situ tests in two main categories. One is the profiling test, in which we obtain the stratigraphy, and then we obtain parameters through correlations, okay? And the other type of tests are the calibration tests, in which stress and deformation are known, and parameters are obtained through numerical analysis. This is rigorous, and this is empirical, okay? Profiling tests that we use a lot are these here: SPT, CPTU, which is the piezocone, magnetic dilatometer. I'm not going to talk about this in this lecture, and Vinci test, although a lot. These tests results are analyzed through empirical correlations. And then we have the calibration tests. The most important of all is the back analysis of trough embankments, which I'm going to address in order to test ground improvement methods. We have the pressure meter also could be analyzed through a rigorous method. I'm not going to talk about this. Self-boring pressure meter also. Menar pressure meter, more or less the same. Also, we can analyze through rigorous mathematical analysis. Plate loading tests, horizontal plate loading tests. I'm not going to talk about this. I'm going to talk just about back analysis of trial embankments. And it's when you plan a site investigation program, what you must have in mind is the variability of soil parameters. When you carry out an SPT, the variability is very, very high. And the coefficient of variation could be up to 60. This is inherent, is in connection with the type of test that we do. The mechanical cone also has a higher variability. We no longer use mechanical cone. What we do use are CPT, vane shear, DMT as the main tests. These tests are used for other applications. Usually I don't use these tests for soft soils. Anyway, as you see here, the CPT and the dilatometer, they have a very small coefficient of variation. They have a very good repeatability, which is not the case with SPT, and it's not the case with Vinci testing as well, as I'm going to address later on. The other thing that we should have in mind is variability of soil properties. And what is the worst is the coefficient of compression in the odometer test. This has a large variation, especially because we have a very influence of soil disturbance, which I'm going to, sample disturbance, which I'm going to address. The drain strength also has a large variation. I'm going to talk about that. However, for instance, the unit weight, the coefficient of variation is usually very small. Also, when you're dealing with drained soil, that you want to have the drainage friction angle, both the phi and tangent of phi, they have not very large variation. Water content is less, limit is medium, but void ratio is large. But what is striking is these properties here have a very large variability. Okay. This is the old SPT. This picture looks like to be from the 50s, and they use very simple equipment like that. Everything was done by hand. This is not anymore. And today we have automatic SPT usually. But this was the start. This was developed in America, and later on it spread out to many countries. And this is an example. Okay. And drilling and sampling. Usually, when you have a soft clay, we're talking about tube samplers, which I'm going to address. And then when you hit harder soils, these are the tube samplers, which are used in very soft soils. And these samplers, they have to be wall thickness very small in order to, and also some other properties which I'm going to address, in order to reduce the amount of disturbance to the sample. If you have hard soils, you use Denison, SPT, etc., and rock, of course, rock sampler, which I'm not going to address. The SPT sampler, which was probably one of the first to be used back in the 30s, it's still a very useful test, but the quality of the sample that it extracts is very, very low. And we get only very disturbed samples, and these samples are obtained through striking with a number of blows the sampler, and these are the diameters. The external diameter of approximately 50 millimeters, and internal diameter is 35. So this is a thick wall sampler, which does not yield a high quality sample, just the opposite, it's very disturbed. And usually for soft soils, this doesn't work. Why? Because this is a typical example of a project, a very big project in Guyana. It's a big bridge being built in Guyana. And here we have about 6-7 meters of depth of soft soil. And what's the SPT in this very soft soil? It's 0. This is why we need other tests in order to be able to extract information from these soils. And why we can't extract information with SPT very low? Here's an example of a very good correlation, which I have used many times. The SPT number, which is the number of blows to install, to drive the sampler 30 centimeters or 1 foot. And when the SPT is very low, which is the case of soft soils, you have a very wide variation. You get anything that you want. So SPT is very important to see what's the depth of the clay. Okay. Also, it gives some information about if you're going to use foundation here. This information could be very important, but only for soft soils, this is not enough. And what do we use? Tube samplers. Okay, this is a shell tube, is a thin-walled tube sampler which protects the idea is to obtain a high quality sample. And what usually these tube samplers have? They have a kind of a valve here which allows the water to come out. And when you tend to extract the sample, sometimes you have to apply a rotation to cut this bottom part here for you to be able to extract the sample. Then this ball valve leads to a vacuum on the top of the sample. It closes, leads to vacuum here, which enables you to extract the sample. There are other variations of tube samplers, but long ago, very long ago, I have done a research project on the different on the quantity of the sample by varying the diameter of the sampler and the diameter of the specimen. I used from 50 millimeter in diameter samplers to 125. This was more sophisticated piston cone. I'm not going to address all the details, but what I found long ago is the larger is the sample, the better are the results. However, it's important that this is undrained strength profile and depth. And if I use a small diameter, that's the kind of average value that we get. very low. And as we increase the diameter, of course, there is some scatter here, which is not presented, but these are average values, okay? But we see very clearly that once we increase the diameter of the sample, and we have, even if you have small diameter specimens, the quality can be much better. So for me, the most important characteristic of the sampler is the diameter. When you have large diameter, you get much better sample. Of course, there are some other features like error ratio, etc., we're not to discuss, but for me, the most important one is the sample diameter, okay? CPT. We're going to talk a little much more about CPT because today is the main type of test that we do in soft soil together with Vinci as well. So we are talking about the CPT. CPT is the cone penetration test, and it was developed long ago in the 30s by the Dutch, and I'll explain why. So we just talked about SPT very briefly. Now we're going to talk about CPT, and later on we're going to discuss the Vinci test as well. Anyway, the reference to this, I'd like to recommend two main reference. One is this Guide to Cone Penetration Testing by Peter Robertson. He's a specialist on this, did a lot of improvements to the test, to the analysis, and this is available on the internet. The other one is from a friend of mine, Dr. Fernando Schneid. He has a book on this, which is very good. And I recommend both reference for you. History. The CPT was developed initially in Holland, and the first one to carry out tests was this guy, Barendsen, and he used a simple mechanical cone. Later on, after the war, Houtsche, he started making it's a there was a machine shop in Holland, Houtsche Maschinen Fabrik. Houtsche developed a mechanical cone which was very much used. Later on, 1947, Vermeiden, a metal cone which had a local friction device to measure local friction. But the main advantage the main development was in 1964 when Fugro developed probably the electric cone, and that's what we use today with some additions, which make the cone a very, very important tool. Bergman developed a sleeve friction cone that was a mechanical cone, and Torstensson was the first one to use the piezo cone. He's from Sweden. And in 1984, the last, I think, development was at UBC. Professor Campanella and others, certainly Peter Robson as well, they developed the seismic cone. And why this was first used in Holland? The reason is very simple. Holland has a very, very soft soil. So to the point that the first 30 meters or 20 meters of depth, the SPT is zero, absolutely zero. So that's why they developed something much more sensitive and could be applied to soft soil. And how the cone looks like today. Today's piece of cone, we have three measurements. We measure the tip resistance in this cone, is a 60-degree. We measure pore pressure. Usually, there is in most cones there is a porous element here and a transducer, in which allows to measure pore pressure at this position. Later on, I'm going to talk about this position, U2, if that's the name we give it to it, and local friction, which is measured at this sleeve. Internally, the cone has at least 2 load cells and pore pressure transducer here. So this is the pore pressure transducer. Here, there's one load cell that measures the cone, the tip resistance, another one that measure the slip friction. Sometimes we have additional cone in which these only measure tip resistance, this measure both tip and friction. So we have to subtract the tip measurements in order to get the friction. Okay. Standards. There's a lot of standards. The American standard is okay. I have been using American standards with success, and but there are many: European, Russian, Egypt, Norway, Sweden, Spain, etc., etc. Okay, so also international standards developed by the International Society of Soil Mechanics and Geotechnical Engineering. Okay. This is the first CPT that I carried out. I was from 1978 until 2023. I was an academic, and just before I joined the University of Rio de Janeiro as a professor, this was a thesis which I was somewhat involved. It was a friend of mine who did this work, and he made, that was his thesis, he developed or designed a cone, and also this was the data acquisition system. In those days, we didn't have digital systems, digitalization, so we used the paper plots, very expensive, this equipment, but that was what was available in those days. We didn't have the digital system. And so the piezo cone that we have made a lot used, we have the screen friction, pore pressure, as I told you, the tip resistance, the wheels of a truck, the cone is just entering the soil. And this piezo cone that we have developed later on in the 90s, we designed and built our piezo cones. They have a capacity of 50 MPa or megapascal of tip resistance. And this is okay for most soft soils as well. And this the data acquisition system. This was part of my research at the Federal University of Rio, and we developed with the electronics laboratory. At the electronics laboratory, this was an electronic guy who worked with us to make this data acquisition system. And then we had everything digital. This was mid-90s. And this was like the front screen, what the operator could see on his screen. This is inclination, this tip resistance, lateral friction, and pore pressure. Okay, so here's the depth, this rate of penetration, and this inclination. We want to make sure that the inclination was not very high. So this was technology of the seismic. In 1975, when I first carried out this kind of test, we used this mechanical rig. Now, it was a rig developed initially for the mechanical cone, but that's the one we used for the electrical cone as well. Very simple. Okay, just kind of a rack with it was manual operated. Later on, I spent 1 year in 1991 at UBC, and UBC, University of British Columbia in Vancouver, Canada, and as I was a visiting professor there, and I had this opportunity to work during a long time in this truck, the CPT truck they used to have in those days. So it was a major development. First time I worked in a truck like that. And I learned also, I'm not going to talk very much about this, but I learned how to carry out the seismic tests. And this was the hammer that was used to generate the shoe wave velocity in the soil for the cone to detect. And I learned a lot at TBC in those days. And this was the uh, first time we carried out some seismic tests in Rio, and it was a research by university, the Catholic University, and I was one of the supervisors, also a co-supervisor of this research. Very interesting. And also, during this with company TerraTech, we have done a lot of tests in many places, many projects. This was a big dam in Ecuador, 2003. We just took the cone with us, and we used a local adapted hydraulic system to push the cone in. It was a very interesting project, and these tests were leads to the decision of not excavating there was a big sand layer here, and the question was to excavate this layer or not. And these tests were fundamental for the decision of not excavating this layer. So this how the project was carried out in a very remote site in South America. So we have to this the umbilical or wire to the cone that we have to pass through all the rods, okay? And this the cone being inserted into the ground. We had also in 2007 a very big project in Peru. It was a mining site and also had to adapt, but this was a much better drill rig, very large drill rig. And we adapted this one to carry out the seismic cone. And I spent some time in Hong Kong as well. And what's interesting, I did some work in this truck belonging to Fugro. What's interesting is that this looks like to be the same truck I used well before when I was in Britain in 1982 to 80. I worked for Fugro in 1983, and this looks like to be the same truck they used in those days. And I had a chance to 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 work in this truck in Britain, later on in Hong Kong at the same truck. And this was for the World Trade Center, no World Trade Center, World Sports Center, something like that. They were building in these days in the Hong Kong island. And this was the most sophisticated truck I've ever seen. In 2002, it was a visit to Holland, and they had this truck with tracks, so it could go to terrains that usually we wouldn't with tires. So a very sophisticated equipment, and everything is automated. Very, very, very interesting. This is the most sophisticated truck I have ever seen, and very interesting. It had two hydraulic systems so that we don't have to stop the driving. The pushing was automatic. When one was going down, the other one went up. So the chuck, that's the clamp. We used to call this the chuck. And so this was a very fast system that just required one operator and very, very effective. And this is the data acquisition system, very sophisticated in 2002. When we did our cones, of course, we had to calibrate them, and we designed and built this calibration frame. And so we could calibrate our cones every time we have a new project, we could do an in-house calibration. And we did this a lot. Also, what's very, very important is the porous element saturation. This is not simple. I'm going to talk about this. You have to ensure that the porous elements are saturated. And what we used to do, this sonic bath to clean parts. Usually we put in the sonic bath the day before. Then we left in this vacuum system. This is something that I remember I didn't know how to buy or to find one. And then I went to my dentist once and I saw this kind of equipment at the surgery. And I was fascinated. Well, that's what I want. That's what I'm going to buy. So we bought this and used this for saturation 24 hours before with vacuum. We put the porous stones in water and we apply the vacuum for 24 hours. Okay. Oh, saturation is so difficult that I had a big lecture with the late Professor Campanella at UBC. And this is what I learned with him. First of all, we should use a funnel upside down, and we put usually don't use water. We use a mix of glycerin and water, 50%. Also, previously subject to vacuum to extract the bubbles. And that's what we do. And then we remove the tip and you use a syringe to saturate this cavity here just above the the transducer, the pore pressure transducer. Okay, these are very important step in saturation. And here some picture I have taken in 1991 from Professor Campanella teaching me how to do this the saturation in his truck. Okay, so that's the funnel. He was preparing to do that, and this is he pulling this up in order to do the he's extracting the tip now, and now he's putting the water mixed with glycerin, previously subject to vacuum in the laboratory. And then the syringe allows him to saturate the cavity. And now the cone is ready. And usually we use a preservative. It's a membrane, latex membrane that we buy anywhere in pharmacies in order to keep the saturation before the cone is pushed into the ground. So I learned a lot with Professor Campanella and passing this information to you. The other thing that Professor Campanella contributes a lot was he realized the difference between the importance of unequal end areas. And why? This is a cone, okay? So here is where you have the pore pressure measurement at position U2, which I'm going to address later. And this is the area of the face of the tip, and this is cross-section area behind. And when he told me that he realized that once he saw someone installing this type of cone with a very large diameter, someone decided to install this kind of cone in soft soil. Why? The idea was to improve the force here and to have better results. And so this led to his discovery of this problem and how to deal with that. The unequal end areas is also we can see in the mantle to measure the sleeve that we use to measure the shaft frequency. You may have this, but this is not correct. This is easy to solve because all you have to do is to have this diameter, this area equal to this one. This is easy to do, but there were in the past some cones with this problem. And so what happens with the cone? Professor Campanella told me that he did a project with Fulgro at some time. And when the cone was zero, before we insert the cone into the ground, we have to zero the data. I mean, to to record those initial values in order to discount this from the measurements. And in this project that he worked, he before the cone entered the water depth, it was zeroed, and then they installed the cone up to the seabed, and before going into the seabed, they had to redo this zeroing in those days, certainly by analog devices. And he thought, no, it can't be true, because we need to, if we are right, we should have the zeroing that we do on the surface would be the same, and it was not. And then what he did, he devised kind of a vessel here in which he could apply pressure, water pressure to the cone and see the results. And what he got that if these areas before and a tip and sleeve, the back, if these areas were equal, we would have a 45-degree line, okay? But it's not like that. And then he came up to the conclusion that there was an effect of the unequal end areas of the cone. Why? Because we have this, it's impossible, let's go back there, here, because of this difference here. You have the pressure, downward pressure here for do the water pressure, and water pressure also applying a vertical thrust. So we have to calibrate to know this A value. In most cones, good cones, this A value is 0.8, and by knowing that, we can carry out a correction. This is what Professor Campanella came up with. This is the corrected value, and this is the measured value. This is the pore pressure measured in this position, and 1 minus A. A is the area ratio, in which in most cone is 0.8. This made an enormous difference in the correlations, etc., because until then, by using QC, we had a much larger scatter. And when this kind of correction came up, they were able to reduce the amount of scatter in the correlation and get much better results. Also, this U2, which the pore pressure measured here, this position, is absolutely necessary. Today, most standards require that if you want to have pore pressure measured in other place, okay, you can do, but this is compulsory. You have to measure the U2 here in order to be able to do this kind of correction, okay? There's a lot of problems regarding the pore pressure measurement quality. If you use a system which is not fully saturated, that's what we may have. We can see from the results, there's a poor response with wrong pore pressure values. The improvers, these always very poor. If we have, in this case, for instance, as you see, when you start the cone, start pushing the cone, in this region, the pore pressure are not very good. And then after, say, depth of 10 meters, for instance, we start having a much better response. And why do we know that? Because of the variation. These are the kind of scatter that we have when we push the cone with a well-saturated pore pressure west saturation, porous pressure cavity. And this is a very good saturation in which we have all these small variations, okay? And this is very clear detection of thin layers and seams. And some soil deposits, they may have thin layers or seams. And for consolidation, to know whether or not this is present, the seams, sand seams are present, it's absolutely necessary to carry out CPTU with a very good saturation of the pore pressure elements. However, sometimes, even if you do a very, very good saturation, which is the case here, you may have cavitation. What's cavitation? When if you push your cone towards a very strong, usually over consolidated clays or dense sands, you may have a negative pore pressure increment that leads to cavitation. And we don't have a solution for that. Usually what you have to do is more than one borehole, one that you measure the pore pressure at the top, the other one we drill out and start from the bottom, and you have two boreholes, and then you put the results together. And in our experience, we should have not only to do a very careful calibration, but not only this. This is a case in which we did some field tests in order to check the quality of the saturation. And here, for instance, in this case, there was loss of saturation, very clearly loss of saturation here, and then at some stage it became saturated. What did we do here? We pushed the cone from the ground floor, ground level. After we did some experiments, because the water level was very close, say 1 meter maximum from the ground level. And then what we did, we drilled out, say 1 meter, half a meter, usually 1 meter, put water in the borehole, and then we did another cone, and you see we got much better results. Okay, so since this project, which took place long ago, we always carried out a small borehole, filled with water, and pushed the cone through this small borehole. And well, let's discuss a little bit stratigraphy. In the early days, interpretation was done like that. If you have sand, that would be a very large QC. This is the time of QC, not QT. QT came much later, in I think 1989, something like that. Anyway, QC, if you have sand, you have a much bigger values of QC. Then clay, reduce, sand again, it has big one, and this very small. Later on, when they started to do, we never use important to say, we never use the friction ratio alone. We use a relative friction, which is the friction ratio, which is the FES, the friction, measured friction, divided by QT. And this was some tests we carried out in 1991. I was involved in carrying out this test in Richmond, British Columbia. And you see here, this is certainly, according to the previous interpretation, very easy to see. This is sand, which very high values, up to 30 megapascals. And then it enters soft clay or soft silt, where we have very low values. It's interesting to see that here we have sand seams. Why? Because we have a sharp increase in the QT, and this is also observed with a reduction odds of pore pressure, measure pore pressure. Okay, so this is U naught, the original uh, original value, the water level, the existing pore pressure in the ground, and this is the measure pore pressure during the contest. And looking at this stratigraphy, we may easy to find where we have sand, where we have sand seams, etc. And this is the way we used to do back in the early 90s. This another project I've been involved in which we could detect a clay seam here with increased pore pressure, okay, increased in RF. Every time that you have very big RF, it's clay. I'll show you later. And this QC, this FF. FF is never used alone. What we use is the friction ratio, which is FES divided by QT. But this is old, so we still have QC here. Very old data. This is one of the first soil classification that came up. This work was Campanella, Roberts, etc., the UBC people. And they did a very, very good work in which we have this QT and RF. So as we go this way, as we increase the friction ratio, it's because we have more clay. Okay, this is lean sand, clean sand, and this is clay. And in those days, they thought the pore pressure could be used as soil classification as well. But what we found later on in the later methods, we decided not to use the BUK because the BUK can be affected by measuring problems, and then this was disregarded. This kind of classification system was disregarded much later. And so at some stage in between 91 and in the 90s, late 90s, Peter Robson came up with this classification, QT versus friction ratio. This is a very good one. And also he standardized the colors in order to plot the graphs, which makes very easy to look at the colors and you know which type of soil you have in most cases. And also, I remember I used to write my own software at some stage, and later on appeared lots of very good software. And today, what we use is this CPTIT by Geologs Mickey. I have also helped the developers to. I have done some tests, etc., and some ideas. Have been working with this for over 10 years, more than 10 years, nearly 20. And also Sleek is the same software house. And we have there are others also. The SPAS, it's a software which I helped to develop to analyze the seismic cone. And these software that I use are from this Greek company, which I have been working with for a long time. But there are other software, so it's a question of choice. My choice was to work with these guys. And this is how I did the data process in 1991. I used a software called Sigma Plot, and I did my procedure or programming. I could do a programming, and it could plot. We could have very beautiful plots. And later on, when I start using CPTIT, it's much better now. So that's the software I use, and I recommend anyone to have a look at this software. It's cheap and very, very reliable, very good. This is what I use. And and also this software has a lot of lots of correlations, inbuilt correlation, so that we can estimate parameters through these this software. I'll give you an idea of, for instance, how to one of the main advantage of this kind of software. that we can use to obtain settlements. And these are deformation moduli from the past. The first to do that was a guy called Sangler, and he came up with these alpha values, these relating Yambus model, one-dimensional models to the QT, E50, Gmax, etc. I'm not going to talk very much about this. This is what the work of Sangler in 1972, a very good book which I read many years ago. Later on, Kuhau and Main provide this kind of correlation to get M, and still later, these are correlation from Dr. Robson in 2022, and this is what is inbuilt in the software. And these are settlement calculations. These calculations are carried out delta sigma V, the surcharge, this the sublayer, and this the modulus M. And my experience using this kind of prediction is that this is very, very reliable, to the point that, for instance, in the late 80s, the diatomic was the best method to calculate settlements. And today, I think the analysis was very well developed, to the point that we have the cone yields very good results. I'll talk a little bit about dissipation test. Dissipation test is when you stop the cone penetration and you measure the pore pressure, and then you plot square root of time in seconds, and you have this kind of curves. So here we have a high pore pressure, and this some time later, what you have here is the groundwater pore pressure. Okay, this is the generated pore pressure during penetration, and then of some time after dissipation, this is the groundwater. So if we stop the penetration and leave for some time, depending on the permeability of the soil, you're going to get the groundwater pore pressure at that position. Okay, if you have, I'm going to talk later on, if you have a collapsing soil, which not collapsing, compressive soil that compresses during penetration, then the pore pressure decreases. But if you have otherwise a soil like sometimes a very hard soil, a sand soil, that dilates during penetration, and that's what the pore pressure may increase. And here is a soil with a very, very high permeability that doesn't dissipate at all. These are sand, okay? So the importance of looking at dilation compression. Let's see, dilation is when you carried out a kind of a test, a triaxial test, and the volume expands. And what you have, for instance, these are grains, soil grains, and if the soil dilates, what you have, the volume increases and the pore pressure decreases. This is what happens with dilation and contraction. Contraction does the opposite. Is when the particles tend to come more closely together, and then you have a decreasing in volume and an increase in pore pressure. Pore pressure is just the opposite to the tendency of dilation and volume change. And these are CPT designs. This was the first CPT design designed by, I think, Torteson, I don't remember. And then today what we have is, this is what Campanello did. He named the position, this position 1, this position 2, this position 3. And from during a lot of time, this was, there was an argument. Many companies want to have, Fluger, for instance, want to have position 1. Others want to have also position 3. Today, most standards require that we use the position 2, that's the U2, if you want, and allow you to have pore pressure measured in other position like U1 and U3. And this is the radial consolidation solution. I'm not going to discuss because we are late in time. And what you use is always the solution, which was published in 1988, in order to calculate, to analyze the result from the dissipation test. And here's how we analyze the dissipation test. This is the dissipation test, tending to stabilization, tending to the groundwater level, groundwater pressure. And we put a line here. We extend the line to U naught. We extend the line to U until U100. And what we do is we calculate the T50. This also I learned with Di Campanella long time ago. And this is the way, once you have T50 through this graphical method, and we use this kind of equation from Hosby T, and to carry out this kind of analysis, T50, which is to position is 0.245. This is the radius of the cone. This is the rigidity index or stiffness index, G over Cu, which is obtained from other parts of the in the program, and T50, that's what was obtained through the graphical method, and then you can calculate. I always do calculation with a square meter per year, because then we have high number, and which is very easy to remember. Well, the database that we have had, we had tested many places, South America, Central America, North America, and we have this kind of database in which we anytime that I have a new value, I always come to this database and check whether or not that could be accepted or not. Usually, for instance, why this clay here leads to a much higher, because the origin is related to the mineralogy, and origin, these are alluvial clay, and these are marine clays that most of the time they are very close values. And well, let's go to vein shear test. After this, we make a quick break. History, it was first used in 1919, and Skempton did a lot of tests in 1948. The first test I was in Brazil were carried out by my professor Raimundo Costa in 1948, and also this another professor that carried out more or less the same time. I did an interview with both of them long ago, some 30 years ago, to try to find out who was the first, and they didn't know. So they started using that. In 1950, the SGI, Swedish Technical Institute, launched a very good equipment. And from 1974 to 80, we did a very large, a very big research project financed by the Road Research Institute. And I was part of that, and I'm going to talk about this. Later on, this was a work by Roth. I don't remember when he did that, I think 1988. And he discussed the stress distribution along the vein. And he took examples from other researchers that suggested that the stress distribution should not be rectangular, should be with this kind of shapes. And he did a very interesting work comparing the assessment he did in 1984, Roth. But after he wrote the paper, he decided, no, we should use the traditional equation, which is then the strength is 0.86 of the torque, measured torque. This is pi. This the diameter elevated to the cube for a vein, which is the height is twice the diameter. And how we carry out this kind of test? We usually carry out an undisturbed. We insert the vein. We carried out an undisturbed measurement, and then we apply manually some 10, 20 rotations to the vein, and we do another one, and that's what we call remodeled strength. When we did this work for the road research laboratory, we did a lot of research on the vein, and in the beginning we used this unprotected vein borehole, in which we carried out a borehole, we set the vein, we applied the torque, etc. Then we realized all the equipments which were available in those days, like the unprotected vein, but the rods were protected, so we didn't have the soil friction here, the soil rod friction at this part. Later on, we have some equipment with the torque cell, which can be measured very close to the vein, so we also don't have the effect of the friction to the rods. And this is a very good equipment that was initially suggested by the Swedish Geotechnical Institute, in which the vein and the rods are totally protected. And this was the equipment we used so far. And these are results that we published from this kind of tests, unprotected vein in borehole. And what we see, this work we have done long ago, a very large scatter. And why? Because you have two problems. One is the soil rod friction here, which is very difficult to extract, and also possibility of translating of the vein. So, and we did a lot of rod friction measurements with a rod without the vein, and what we found, erratic results. Very, very difficult to measure and to have consistent. And so the equivalent, this is the maximum torque of the rod friction measurements, and the equivalent endurance strength is very high. It's about 3 kPa, which is very high. So we decided to modify our equipment, and we employed mechanical engineers to help us to do that. And based on some ideas which were suggested by the Swedish Geotechnical Institute, we designed this unit, which had no whatsoever friction or possibility of translation. And the results, we did a lot of tests. I think we had 6 boreholes measuring at every 0.5 of 50 centimeters along depth, and we got much better result with much less scatter. And then we come to the conclusion that the American Society, ASTM Society D2573 has a problem. This publication was we published this paper in 1985 at ASTM Vein Conference in Tampa, in Florida. And we were against this, the ideas that came with the ASTM. First of all, they allow this kind of diamond vein or this kind of vein, while we think the vein dimensions should be standard, like 50 or 100 millimeter in diameter, and the height's twice the diameter. And I don't agree with that. And why? Because these may lead to different results. And also, rod friction measurements under no load condition, it can be performed. We don't agree at all with that. It can't be. It's impossible. That's what we found. So we think this standard should be improved. It has not yet. These soft clay properties of these experimental sites, after we have done all this with large sample diameter, with much better quality of the sample, and much better in situ vein sheet testing. In those days, we didn't have the cone yet. So later on, Guillermo, in 1973, I think, he published a paper in which he strongly recommended the vein correction, and vein tests will be corrected, because in some cases, if you use the vein shear profile like that, you may have a factor of safety more than 1. And he published this kind of correction factors as a function of the plasticity index PI of the clay. And these are the lines. One of these was this one is Bierro's idea. This was another paper by this guy, 1903. But we found out not all clays need to that. And the other thing, final thing that I like to discuss before we move on is design profile. These are kind of another site. I have been doing a lot of field event tests with very good equipment, and then the scatter is too large. So how to analyze this data? And my suggestion is to decide for a design profile that more than 95% of the data are above this design, so that you have a very safe design profile. And then whether or not correction should be adopted, this can vary from site to site. I think most cases that you have this kind of design profile, we may not, unless it's proved otherwise, use corrections. And also we have a database from many many locations, and this depth against the endurance strength ratio. And as you see here, this is 0.22 is the very safe profile. But if you have close to the surface, you always have over consolidation to the local variation of the water depth. And this is something that I use to calibrate tests that come from a new project and to decide what is the design profile. Finally, about the site investigation, what shall be the amount of investment in site investigation? This, of course, depends on the risk. And I have done some work on this. In tunnels, for instance, which the risk is very high, we always adopt something between 2% of the total cost to 3% of the project costs. While in embankment soft soils, if we invest something like 0.5% of the total cost, this, in most cases, is more than enough. And the other thing, final remarks, today, what we do usually, we do a lot of CPTU tests. We start with SPT just to have an idea of the depth. Then we carry out CPTU, and we do some vein tests, not many, but some vein tests in order to calibrate the correlation between CPT and vein. Usually, I'm not going to discuss a lot of this, but these initial tests in a project allow you to do this kind of correlation, and this is very important in most projects. Okay, let's have a 2 minutes break before we go to improvement. Okay, only 2 minutes, so very quick. Okay, let's go ahead. Now I'm going to discuss ground improvement methods and what we learned with these methods. Here is a graph with different types of ground improvements, and those with for soft soils, most of them are here. Remove and replace, ground freezing, deep soil mix, sand mix, compaction pond, driveway replacement, drains for consolidation. I'm not going to discuss them all because we don't have the time. I'm going to discuss a few of them, especially I'm going to talk about deep soil mixing. I'm going to talk about drains for consolidation. These are the main types. And how I learned through tri-embankments. I have done the first tri-embankment in 1975, and I'm going to address these which are in yellow here. But these embankments were carried out. The first one, the first two were used for research, and through the Road Research Institute, and others were used for big projects, which I'm going to address. These are tri-embankments that have been carried out between 1975 and 80, and I was involved in these projects. And these tri-embankments close to Rio were used by the Road Research Laboratory or Road Research Institute. They sponsored this research, and that's where I did my PhD long time ago. Okay, this is the soft soil research program, which lasted from 1974 to 81, and carried out by the Brazilian Road Research Institute. And here are where we built our embankments. There were 3 experiments here. One of them was this one, which happened to be my embankment 1 taken to failure on soft clay. And this happened to be my PhD thesis. Later on, we carried out a very long embankment with several sections, 1, 2, 3, 4, 5, 6, 7 sections, each one testing a different soil improvement method. And also there was the access road, which I'm going to address as well. And the failure that took place in 7 December 1977 became my PhD thesis, which I submitted in 1980. And I did a lot of analysis. In those days, of course, we didn't have the programs, so nice, very nice programs like we have today. They were everything in Fortran. So imagine the difficulty, but we did a lot of work. I remember I used to run the programs overnight because we used mainframes, no PCs, no IBM PCs, and I did the analysis with a vein shear profile, the one I have shown you before, and we got a factor of safety of 0.96 at the maximum height of 2.8 meters. The lessons I learned: maximum embankment height 2.8 meters, back analysis with mean and corrected vein shear testing, strength yielded factor of safety of 0.96. Bierman field veins correction may not apply unless you reduce the strength, of course. The VST equipment improved to avoid friction and translation of the vein. This was a very important finding. And all the instrumentation were locally made, except the inclinometer, which we bought, I remember, from Cinco. The rest were all our local design. Then we carried out the second embankment. The second embankment was to test ground improvement methods, which were recommended in the 70s. So long ago, in the early 80s. Okay, so this was the embankment built up to 2.5 meters below the failure height, maximum height. And we have a lot of instrumentation like settlement plates, full profile settlement gauge here, we had piezometers, we had these were hydraulic piezometers, twin tube piezometers, inclinometers, magnetic sensometers, and all our, except the inclinometer, of course, all our local design. And we tested the methods which were used in those days, like sand drains, open-ended method, okay, jetted sand drains, which people thought it was very good, and weak drains. Weak drains in those days were the starting points. I don't remember that we used that before, and this is the weak type of weak drain that we use. Installation methods, which the weak drains were pushed alongside a rod. We don't use this anymore. We know that this is bad because it may smear the sand drain and prevent the use. And someone had a very good idea of using no woven geosynthetic weak drains. And in those days, we thought the permeability would be high enough to bring the water to the surface. It didn't. And it took us some time to realize that, because the horizontal permeability of these kind of woven geosynthetic is very high, but the vertical was not. But we learned this later on. And these are flow pressure measurements that were taken during installation of these drains. I was directly involved in this, designing this system and also taking measurements. And what we found, the closed mandrel yielded the highest pore pressure. The jetted a little bit less, okay? And the geotextile a little bit less. The weak drains, the minimum pore pressure. And this was found the best method. And also we did settlement measurements, and we did a lot of calibration of this. And I'm not going to discuss all the details, but these are very interesting research. I'm going to the lessons that we learned. The jetted drains that people thought was very good increased settlements by 40%. And why? Because it disturbed the soil. Okay, so this was prohibited late after this experiment. Sand drains increased pore pressure a lot, especially closed mandrel. Non-woven weak drains did not work at all, but we thought before that it worked. Composite weak drains yielded the best results by far. So that's why our highways department embraced the idea of using weak drains all the time, and the other method are not allowed anymore. We did also this experiment, the access road. This was published, I think, 1982. And this was a thesis by a very good friend of mine, later on, Professor, Emeritus Professor Enio Palmeira. This time he was a very young engineer. And probably the first time the horizontal strains were measured at the base of an access road like that. The access road was 1.2 meters high, 4 meters wide. We use it for the trucks, for the lorries to dump soil on the embankment, to help to build the embankment. And we carried out experiments using the non-woven geosynthetic with 400 grams per square meter, and the strains at failure were 30%. In the beginning, I thought it wouldn't work at all, but later on it worked. It reduced the amount of, as I'm going to show. And these are the theses by Professor Palmeira. And measure settlements, these are the lessons. Settlements 100 to 200, measure strains 10%. Bearing failure occurred at the control section there was a control section without geosynthetics. And reinforcement effects after 200 trucks passed prevent the bearing failure, reduce settlements by 20%, and reduce embankment volume by 20 to 25%. So, contrary to what I thought it wouldn't work, it did. And why? We only knew much later on. Because when you have stress on the geosynthetic, normal stress on the geosynthetic, they measure the behavior changes completely, and it yields in a much lower strength. So that's why it worked. But this took us some time to realize. This is another embankment we carried out at Juturnaíba Dam. It was a big dam, big in terms of length, but not very high. And here we have 1 kilometer of very, very soft soil. So the designer asked me to work with them to carry out the experiment of this dry embankment. And I designed this experiment, and later on, this was the thesis, PhD thesis for a friend of mine, currently Professor Coutinho in the north of Brazil. And these are the properties. And we had a very large scatter of all properties. And then what was the problem with this project? To put a berm or not. This would, the decision was difficult if we had only the test. And the idea was to carry out this kind of experiment that we carried out. We installed a lot of instruments, and we carry out these tests up to failure, and we use this for the design of the dam. Slip surface located through instruments, mobilizing mean drain strength at failure about 20 kPa. This was unknown before the embankment. Key information, very important information for the dam design, and this led to a much better design in those days. This was 1983, 82, more or less. And this was the thesis, PhD thesis from a friend of mine, Professor Coutinho, today. With drains and temporary surcharge. We used this a lot. These were the results from the experiment in which we place a geotextile. This is absolutely important in order to avoid bearing capacity failure. A sand blanket, weak drains, we drive the weak drains. If the embankment is very high, we have to use reinforcement or not, depending on the case. We build the embankment, we put a temporary surcharge, and later on we took it off after some time. And these are the weak drains that we use so far. And this is the stitch machine that's installed the weak drains. And this kind of solution has proved to be one of the best and definitely the cheaper one. Here's a case where we have the height of embankment, low embankment. We applied a surcharge, and then the surcharge were removed. And the settlements, when we removed the settlements, it stopped. This was a control section which the surcharge remains, and you see the settlement going on. But the one we removed, timely removed, after 6 months, that's the time that it has to be there, usually. When we removed, the settlement stopped. And pop pressure, very interesting. Here's when we install the weak drain. When we apply the surcharge, we have a built-up of pop pressure. And very, very soon, about 30 days after that, we see a strong reduction. And why? Because the weak drains were working very well. We see the efficiency here. Later on, we increased the embankment. There was a stockpile wrongly placed where it shouldn't. But here we see when the stockpile was placed there, immediately there was a pop pressure built out. What's interesting is that I've been to this site 10, 15 years later, and the behavior was excellent. We had here about 10, 12 meters of soft clay and no settlements at all, okay? A lesson that we have learned, and that's what we recommend. First of all, the cross-section of the stitching machine should not be larger than 70 centimeters. Why? In order to reduce the smear effect, to reduce the stubbers. The sand mat should have a drainage. Sometimes when you have a very large embankment, you have to put additional drainage system in order to collect water from the sand mat. Thickness usually 40 centimeters or higher, and always a woven two-dimensional bidirectional geosynthetic underneath the sand in order to protect it and to increase the bearing capacity. This is very, very simple, very cheap. Weak drains, what we learned, spacing in between 1.2 meters and 1.8. Why? If we have a very small spacing, this may not work because one drain is going to affect the other one, this soil disturbance. And usually when it's over 1.8 meters, it may not work as well. The tensile strength of the weak drain should be 2.5 kilonewton minimum. Some projects may require even more. And the weak drain should have a drainage capacity of minimum 1,000 cubic meters of water per year. And little sand seams. If you have lots of sand seams, you may not need, as I've seen this taking place, you may not need weak drains. The sand seams would be able to lead to consolidation. And this is the last one I'm going to address, the Porto Alegre Airport. Porto Alegre Airport is the south of Brazil, this position. And some years ago, they wanted to extend the runway. And we did a lot of pisocon testing in that area. So the soft clays were up to 8 meters, 9 meters deep. These are very, very good tests. Friction ratio, pore pressure, as you see here, the soil behavioral type index, which the program generates automatically. And why we decide to use the deep soil mixing? Deep soil mixing is we mix cement with the soft clay. And what's the advantage of this method for this airport? We don't have the waiting time. Weak drain is cheaper, but the surcharge has to be there for 6 months. They did have this time, and they want to open the runway very quickly. So we did this project with the Keller company, and this is the tool to mix the soil with cement. This is the mixing plant. We did a lot of laboratory tests on-site laboratory to check the quality of the strength, check the strength of the samples. And also we did a dry embankment and instrumentation. I was involved in this project. We did a lot of analysis and we posted these results in America in a conference in 2015 in San Francisco, the FI conference. And what we found is that the mix has to be well analyzed before. We should do a lot of tests beforehand in order to come up with the best solution for the mix. Usually it's the one which uses less cement, which is more expensive. So we had a good embankment behavior, early estimate of cement consumption of 150 kilos. And this was initial estimate. Later on, we found we had to increase cement consumption for 350 kilogram per cubic meter. And need for initial dosage studies. I'm involved in a new project at the moment, and what we're doing a very comprehensive site investigation with lots of tests in order to assess the cement consumption, the best cement consumption for that particular project. Then lessons from someone else's mistakes. Light embankment. Light embankment should be a very, very good solution. Usually we use EPS blocks, very light unit weight of 1 kilonewton per cubic meter. But this was a case in which a friend of mine designed a pilot slab for this approach embankment to this bridge. During the process, the highways department decided to change another consultant came in and he recommended to change, to use the EPS, etc. Very, very good solution as well. But he forgot the possibility of a flood, which took place a couple of years after this was built, and it was a disaster. The river flooded and everything floated, and this was the result. So when using this light embankment, we have to make sure that this cannot occur to the point. But the problem is sometimes it's impossible because we always have floods, that unpredicted floods. So these are very important points. The other thing which I learned from experience is when we place a new embankment close to a new one, we have this kind of crack, longitudinal crack along the road, and this is very difficult to prevent because of we have always differential settlements here which lead to this. Early surcharge removal. This is a case that they decided, we're going to remove it before and see what happens. It was a disaster. Okay, so a minimum of 6 months, never less than 6 months. And also, you have to look at large rate of this case here. They removed with a large rate of settlements. So we have to wait, like the project I've shown you before. Pilot embankment. This seems to be very simple. We drive piles. We put this kind of pipe cap. Then we have sand blankets, geogrid, embankment, and that's it. Seems to be excellent. And someone designing this, I was against this kind of design for this site, but the client decided to go ahead. And what happened was that after that, I went to the site and I saw this was like a roller coaster with lots of valleys and mountains. So a car would go like that. And then they asked us to carry out some excavation to see what happened. And that's what we saw. Most of the geogrid was tore, and a lot of problems we have seen. And it took us some time to realize the needs. This project was completely wrong because when we use this, we should not have sharp edges. We should have rounded in order to avoid damage to the reinforcement. And also we should have a protection layer. And here we put the reinforcement. So hard to learn, and this is the reinforcement that we should use with all this protection to avoid tearing the geogrid. Vacuum consolidation. It works. I know it works. However, this is a project in which I did some analysis afterwards, after the problem took place, and what I saw from the instrumentation results, no pressure dissipation. Why? Also, vacuum. Since there was no porous pressure dissipation, we didn't have any increase in the strength, and the embankment failed. I was involved in the analysis, and what I learned, we have to ensure that the vacuum works. Probably it didn't here. We have to control leaks. We have to use weak drains, but they should not touch the bottom of high permeable layers, because otherwise we suck the water from the permeable layers, not from the soft clay. So no sand seams. And unfortunately, this project was a total failure because the designer did not do a very good work, and there was no site supervision. And because of this, we must have a much better site investigation in order to avoid the weak drain should never touch the high permeable layers, okay? And always a trial banker should be needed to test the solution. Okay. instrumentation monitoring. Which measurements should we take in soft clays? Settlements, horizontal displacements, pore pressure. These are normal. And which kind of instrumentation shall we use? Always settlement plates, a good number. We always, in case of weak drains, we always should check weak drain solution. We always should check the pore pressure in the sand blankets. If it's too large, we shouldn't have additional drainage, and this is important. So we should have a standpipe piezometer here. These are quick response vibrating wire piezometers in the clay and inclinometers. These are very, very important. And standpipe piezometers are very straightforward designs. Many, those I think used in Boston by Professor Casagrande, I think 1948 or something like that. So the water comes into the pipe, and we measure the depth of the water by using a depth gauge. Very, very simple. These are porous elements. And stability control, I have used a lot. Inclinometers and tiltmeters could be used also to control the stability. And what's most important is when you have, this was my PhD thesis long ago, and after the embankment reached 2.5 meters high, it jumped the displacement. You see here, this rotational tilt, it jumped. And this is a very important sign that failure is approaching. So this is the kind of analysis that we can have on the inclinometer data results to see whether or not we are close to failure. Why this is so important? The interpretation is very simple. If you have an element here, and if the slip surface is more or less horizontal, the inclinometer measure the theta angle, okay? So the element here should have a theta, and the beta angle is nil. Why? Because this is more or less horizontal. So the distortion or strength, shear strength is the sum of this angle by the beta, but beta is zero because this should be horizontal. So distortion or shear strength is close to theta, and this is the interpretation that leads us to understand why this kind of measurement is so important. The theta is measured by the inclinometer. Also, here's a plot of distortions against embankment height. These are distortions here that we measure with the inclinometer, and these are safe limits above which we lose control. Also, we had lots of inclinometers, so we could locate reasonably well where the slip surface was, and by using distortions. Okay, this is the result. So the slip surface has to be passing through these points here. Well, we are close to the end, and now I'm going to jump to put some philosophy remarks in, and physics versus soft soils engineering. Einstein proposed a new theory, and many years after, someone comes up and proves he was right. Okay. Well, soft soil behavior is quite the contrary. In many cases, I have shown you, I thought something was right and it proved wrong, and vice versa. Okay, so soft soil behavior should be cannot be analyzed theoretically. We must have trials, and trials, and testing. And what we have to do a good design, a good project, reliable, sustainable, comprehensive site investigation. The essential are CPTU and vent testing. A comprehensive monitoring program is absolutely necessary. theories need to be validated. Some of these projects went wrong because people thought, only believed in theories, believed on the paper, or believed on calculations without field experience. So field experience is absolutely fundamental. If you are testing something new, carry out a trial embankment. This should be my most important recommendation. Avoid intellectual arrogance. The intellectual arrogance that led some of these projects to fail. Why? Some people, some consultants did some calculations. My calculation have to be right, and they are not. Humble approach is only to believe in field measurements and trial embankment for large projects. And that's it. Thank you very much. You have my contact details here. If anyone has would like to have a copy of those books, I'll be very pleased to send you. Also, I use WhatsApp all the time, and that's my number. I thank you very much, and if is there any question, I'll be able to answer now or later on by email. Okay, thank you. No question so far. Okay, thank you. No, there's one. Sand pile. Okay. Well, it's possible. I have used this before. And what I usually do is I tend to encapsulate the sand pile with geosynthetic. I have used this before. It works, but I didn't have the time to talk about all these experiments. It works. Okay, but you have in the past, in the 80s, we didn't have geosynthetic, so it was just sand. No, it may not work. We need the encapsulated sand columns, and we need the geosynthetic in order to avoid the bulging of the sand, especially in very weak ground. Okay, it works. Another one. The question is, I'm designing a soft soil embankment solution. Could we use steel sheeting at the base to cut off failure wedge and concrete blocks to add weight at the base? Well, I never used this steel sheeting at the base. I only use geosynthetic. Geosynthetic works very well, but of course, other materials could be used as well. And I would suggest, if the soft soil embankment solution, I would strongly suggest that you use geosynthetics, okay, because this is a well-known solution and approved solution, traditional solution to reinforce, okay? It's possible to add weight at the base. Yeah, it's possible, but the key issues would be, first of all, you should have a very good sand mat to avoid to have bearing capacity for the equipment that's going on there. Okay, this is fundamental. So you should use always bidirectional geosynthetic at the base, the sand, and then if necessary to put reinforcement on it, you can put. The decision which method you may use to consolidate could be The cheapest one is always weak drains, but you should wait for 6 months. Okay. Then you can have the more expensive one. You can use jet grouting. You can use deep soil mixing. Uh, Jet grouting is more expensive. Deep soil mixing is in the middle. You can use pilot embankment, but you have to take precautions what I have shown you. Otherwise, you may have a problem. Never sharp edges. Use geosynthetic. Also, the pilot embankment is very good when you have the embankment is high. For a very low embankment may not work because you may not have arching effects in between the two piles, the pile caps. So encapsulated sand columns, they do work. Also, stone columns I have used a lot. They do work as well. Okay, but usually stone columns do not work when the soil is very weak. For instance, the German standards require a minimum of 25 kPa strength for you to use sand columns. I have used down to 10 kPa. It worked, but never under 10 kPa. Okay. Could you please specify the property of soft soils such as cohesion, fiber, and capacity? Yes, but I need to, we can do that by having what we need in a soft soil. We need CPT is fundamental, absolutely necessary, and some VSTs as well. Okay, these are fundamental. Once we have that, it's not very difficult to come up with the properties and design values for your project, okay? I'm available to discuss this with you if you contact me later on. Send me some information, I will come back to you. I will write back to you or through an email, okay? Another one. Okay, guys, thank you very much. Remember that I'm on the side of the line, on the other side of the line, and easily to be contacted. Okay. Thank you very much. If there are no more questions, we had 3 discussions, very interesting ones, and uh, thank you. Okay. Bye bye.